Good morning. My name is Owusu Edusei Kofi. I will be your lead instructor for this OEM course on the DeltaQuad Pro. I will be assisted by Max Ashite. He will also be our lead pilot instructor. Max will be joining us in the course of the training. And then we have our software pilot instructor also here, Jed. So Jed will be making sure we have all the softwares that we need for this training. As I earlier indicated, we need to come with our laptops. If you don't have a laptop, I would humbly request that you stretch your neck along your partner and then have access to the materials. Because 60% of the training is based on you understanding the ground control station and how to plan the mission, bring the drone safe back home. In the course of these 5 days training, we will be covering very specific topics. And these topics, as I've earlier indicated, is quite broad. And I will make sure that we're going to get the very deeper understanding. I'm also recording the training so that at the end of every lecture, I can quickly upload it for you guys to have access to it and then refresh your mind on it for the next day. There is a saying that man proposes and God what? Disposes. Our only limitation in this exercise is our weather. So we will make sure that we will keep track of our weather, and whenever we have very good weather, we will be doing our demo flights. Yesterday we were here to collect some local knowledge information on the wind conditions here and the time differences in terms of when the high winds set in. So we'll also be monitoring those environments and then make sure we'll be able to do a very successful flight. We'll be having a set of two groups. It's going to be mixed, both Boundary Commission and Navy. The beauty of this training is that we are working as a partner, we are working as a group. So when it's time for us to kick in the practical session, we'll just do the numberings and then we'll set ourselves into two groups. The most important thing about flying bigger platforms or platforms with mandatory aviation standards is safety. And safety in the sense that we need to be our brother's keepers in terms of our watch. So if you are assembling the system, you don't tell me because maybe he is assigned to assembling a system. Once he's assembling a system, I'm not supervising. Because at the end of the day, if he doesn't fix certain things well and he gets any issue, they don't blame a single entity, they blame the crew. So we will be looking at all those safety aspects. So within these 5 days, we will be looking at the basic introduction to the UAV, and I'm very happy we've covered all the basics in our previous training. We'll be looking at the subsystems. So as engineers or as pilots, and as you're looking at starting or being in this business, every manufacturer has different system structures. And you always have to understand how the system is built. And once you understand the system built, you can understand the limitation and the system's capabilities and adjust your user capabilities along that line. We'll be looking at the basic operations in terms of the flight responsibility, safety, battery operation, camera integration, setting up your camera, controlling the remote controls to make sure you get the best out of the system. We'll be looking at the ground control station. This is called a Q ground control. I'm sure some of you may have used the DJI products. I think in your training we introduced you guys to Mission Planner. But this is a different ground control station that we're going to introduce you to. It has a certain learning curve. Once you hit that learning curve, things get easier for you. We'll be looking at the mission planning strategy. How do we plan the mission in such a way that the mission conforms with the system specification predetermined by the manufacturer? Because once we go off board, the system may not function as we expect it to be. Then we'll be looking at the surveillance control. This training also caters for the Boundary Commission when you guys have your mapping drone. So it is dual purpose. So once you are done with this, you can also apply the knowledge when the mapping drone comes along. So this is the timetable. If you happen to have any issues with the fonts or whatever it is, kindly let me know. So today we are late, but tomorrow we may have to stick to the starting time, 8:30, because we have a very fixed timelines to try and meet. So we're looking at introduction and the preparatory. We're looking at system assembly and setup later in the day after we come back from break. We'll also be looking at the basic operation and ground control. We'll be looking at ground control lab setup. So Jed will be assisting us to set up the labs. And we are decentralizing the training in such a way that whatever materials we give you, when you go home, you can practice on your own. So he will help set it up on everybody's laptop. We will provide a link where you can always download the files, but he will be here to assist the setting up. We will be having our flight test in the mornings because of the nature of the winds. And we'll be doing from ground to sea. So basically we'll be taking off from the ground and then we'll be going into the sea, do the surveillance in the sea, and then we'll come back. So that is our ultimate objective that we want to achieve. So we'll be doing that Wednesday, Thursday. If we get very good weather, we'll continue doing more of that throughout the entire 2 days. On the last day, we will have our exam. It's a written, paper-based exams. Jed, how many questions? I think 40. Okay, so it will be around 50 questions. And then we are looking at just an hour to do that 50 questions. Minimum is 80% mark. I have never believed in exams, but I think when it comes to Ghanaians, we cannot give us that liberty. We should just assess each other and make sure the knowledge is being acquired. And then the final day, we'll be going through the Navy drone policy program. So finally, the Navy has come out with a drone policy program. The Boundary Commission will be part of this strategic session. Sub-Lieutenant Owusu will lead the discussion, and then I will supervise its integration. We're hoping that we can share this information with Boundary Commission, and Boundary Commission, yeah, Lieutenant, okay, please forgive me. Please forgive me. I'm very sorry, sir. I'm very sorry. So that the Boundary Commission can also have their own drone policy program, because I believe that we will not be here tomorrow, and it is best for us to set up systems and structures that will govern how we use these machines if tomorrow we don't find ourselves in the same institution. Okay. Great. So we're going to look at the DeltaQuad Pro. The DeltaQuad Pro is a flying fixed wing with vertical takeoff and landing capabilities. So basically, when you look at the limitations with traditional fixed wings or multicopter, we know that fixed wings can give us long endurance. Multicopters provide us with very simple structures in terms of vertical takeoff and landing. Yet these systems poses some kind of limitations in terms of its performance. Human demands for performance on this system increases every day. Application is changing. And when you look at these limitations as well as its capabilities, the human needs and its environmental challenges requires some kind of a hybrid system. And today's hybrid system is either driven by power combination or structural combination. This is our first ever VTOL that we're going to look at. And this is purely based on structural combination. So what this means is that we are combining two different systems to help us adapt to a certain operation. So we have the fixed wing where we are flying with the wings, and we have the vertical takeoff being enabled by the multicopter components that has been attached to the drone. Another type of hybrid system will be we combining an electric fuel system plus a battery fuel system, right? So with this training, we are purely looking at a structural point of view in terms of having such an enhanced system. The beauty about the DeltaQuad is that it's a fully autonomous system. It's a fully autonomous system. Whatever decision the drone has to do is pre-planned and given to the drone for the drone to execute it, whilst you, the pilot, controls whatever execution that the drone has to follow. It's a 4+1 configuration. So when we say a 4+1 configuration, what we mean here is that, let me just so basically we have 4 lifting motors that we find on the wings. And these 4 lifting motors do not tilt. In certain environments, you may have a tilt motor. So this is a non-tilt 4 lifting motors. And then we have 1 pusher motor, which gives us what? A forward flight, or the forward transition flight. So when it comes to the structural design, we have so many combinations. We have 4+2, or we have 4+2 non-tilt, 4+2 tilt. In certain environments, you may still have this pusher motor here, but this one will tilt to give you 3 motors to push the aircraft forward. Different designs, different purposes in terms of its operational needs. So let's have this in mind. It's a 4+1 configuration. 4 motors for lifting, which are found on the wings, and then 1 motor at the back, which does what? The pushing. The operational duration is 110 minutes. This is what is stated by manufacturer. As pilots, it is always important to have certain operational management in mind, and we will not change, or we will stick to these operational rules. If you have a very, just a second. So we have 110 minutes of flight capabilities. The standard practice is that we're going to use 70% for full operation, and we're going to keep 30% for emergencies and landing support. So in as much as the manufacturer is telling us that we have 110 minutes of flight time, we don't need to use the entire 110 minutes for operation. So 70% of this is going to give us around 77 minutes. So when you do the difference, that is what you're going to keep at the back of your mind. That whatever range you find yourself, whatever altitude you're operating, this is the minutes you have to keep the aircraft in the air. This is ideal planning. An environment can really impair this 70% performance. And these conditions, which you cannot determine, one of them is winds. So you may take off at the very beginning of your flight, everything looks steady, and all of a sudden, there is a serious change in wind conditions. the drone has the ability to actually fight and keep being in the air. But once it's still doing that, it's going to burn more of its power. So you should always have that in mind. And especially if your environment is a bit adverse. So you should have this. In terms of its operational capabilities, we have the internal radio, external radio, and LTE support. So we have 3 communication infrastructure on the system. Now the internal radio is basically the handheld controller which communicates with the drone directly. And that is giving you 30 kilometers. The external radio is an external signal booster or an amplifier that is attached to the controller to extend the communication range. One will ask, why do we need an LTE system on the drone? So when you look at directional and omnidirectional communication, especially in urban environments, our biggest enemy is multi-path propagation. So what this means is that with multi-path propagation, you tend to lose signal in a more built-up area. Because at the end of the day, when the drone is flying, the uneven surfaces, the human activities, the channel interference. So let's assume we have this board. We need some protection on it. Let's assume this is our drone. The pilot is on the ground with the controller in hand. We have our built areas. So the communication hits these infrastructures before coming to the terminal, right? Ideally, with a free space, we're supposed to kind of get something like this. But the pilot is stationary, but the drone is not stationary. As the drone keeps moving, the channel conditions along the signal propagation changes, especially in a built environment. And this tends to what? Attenuate the signal as it flies. So in a built environment, another type of communication infrastructure is cell sites, or the GSM or the 4G infrastructure. So you know you're going to have these issues. You can also push the signal through LTE infrastructure and still get it to come to the pilot. So that's why you have the LTE infrastructure on it. If you take LTE to the seas, you're not going to get very good signal. So whatever terrain you tend to fly, you look at it, the communication infrastructure limitation there, and then you can switch based on the signal interference, whichever way you're going about it. It has an ADSB out. So ADSB is basically the communication from the manned aircraft to the tower at the airports, right? Since you will be flying at very high altitudes, as pilots, you need to be very aware of your environment, the kind of aircraft that is flying around you. So the ADSB out allows you to get the real-time position of the manned aircraft as well as the flight height of these aircraft. So when you happen to be in a certain airspace and you are flying and manned aircrafts are coming in, you know the altitude at which they are coming and you know their position with respect to your aircraft's position on your ground control station. So you could pause or you could divert your flight so that you don't interfere with the manned aircraft. So these communication infrastructures, we need to know about them. The payload which is on board the drone is the Nighthawk V2 camera. It's a 3-axis gimbal retractable payload. It has an RGB, black and white thermal, autonomous tracking capabilities. So we'll be exploring all these functionalities with the system. Now let's look at the dimensions or the specifications of the system. So the wingspan, that is around 235 centimeters. It's 90 centimeter in terms of its length, and the height is 17 centimeters. The wing area is 90 squared diameter. The payload bay is 20 by 12 by 8 centimeter. The DeltaQuad comes in 3 variants. So we have the DeltaQuad Pro, the DeltaQuad Cargo, the DeltaQuad View. So in our case, what we have here is the View, which is the Pro, which is the surveillance platform. I think the Boundary Commission will be getting the Mappa, which is the other variant of that. And then there is the Cargo, where you can use the drone for package delivery. In countries like Malawi and other places, they are exploiting this for blood deliveries. And you can see that because of its vertical takeoff capabilities, this best suits both urban and rural logistics supply, because you can land in any small area that you find yourself. The carry case is 114 by 48 by 44 centimeters, and the flight case weighs 25 kg, which includes the vehicle. Please, one will kind of ask, why do we need to keep all these dimensions in mind? The funny thing about these systems, or these custom systems, is that, especially with flying wings, a little change or you altering anything on the system will purely affect the system's performance. So maybe tomorrow you realize that your batteries are not doing good, so you decided that, oh, I found a battery, should I put the same battery on it? A little difference in the battery weight would definitely affect the aircraft's performance. Even in terms of the dimension of the battery, it will affect the aircraft performance. When you have an empty aircraft, you're looking at 3.3 kg in terms of its weight. And if it is empty, including the battery, now it goes to what, 5 kg. So without a battery, it's what, 3.3. If you include the battery, it's what, 5 kg. The maximum takeoff weight is 6.2 kg. And the payload capacity is 1.2 kg. So if our maximum takeoff weight is 6.2 kg, which components contributes to the aircraft maximum takeoff weight? So the aircraft is ready to take off. We have a maximum takeoff weight of 6.2 kg. So what are the components that constitute this maximum takeoff weight? Yeah. No. So you have the aircraft itself with the battery plus payload. So you're looking at 5 kg plus 1.2 kg. And this weight is pre-calculated according to the thrust of the motors. So if you go above 6.2 kg, the aircraft will have challenge in terms of lifting up. Or it may lift up, but you may burn more power. So the 6.2 is our cutoff point. Manufacturers have a way of playing mind games with you when you don't know what you are doing and there is a problem. I know somebody who has lost his warranty on his aircraft because he kind of went overboard the set maximum takeoff weight, flew the aircraft, and there was an issue. He sent a log to the manufacturer assessed the log, and he said he flew the aircraft above the recommended weight, and because of that he has lost the warranty. This company also has that system. So we need to be very cautious about that. when you have a payload inside the aircraft, it flies with a different dynamics. And when you don't have a payload inside the aircraft, it also flies with what? A different dynamics. So let's look at the flight characteristics without payload. So let's assume there's no payload in there. So mostly, if you've done some bit of communication, you will notice that typical manned aircraft or drones have this kind of a dumbbell-shaped fly path, right? Mostly we attribute this region to our takeoff and our transition. We have our cruise, we have our approach landing, and landing. Can get some assistance during the break for the board, it will really help. Because I doubt if those at the back will see what is happening. Okay, so the DeltaQuad has an operational pitch angle of plus or minus 10 degrees. So that means that when it's climbing here, in the positive direction, we are between 0 degrees to plus 10 degrees. Okay? When it's in the cruise state, it completely uses what? 0 degrees. When it's landing, we are looking at minus 10 degrees. The manufacturer insists we keep the aircraft within this pitch range. When we go outside the pitch range, what we're going to have, the issues are going to be that you're going to burn more power in terms of recovering when you go too deep or when you go too high outside this range. Now, when you don't have a payload on the system, you have a cruise speed of 18 meters per second. So that is when you are in this range, that is your speed. When you find yourself in your stall speed, you have about 40, that is 12 meters per second, which is 43 kilometers per hour. And the maximum flight time is 2+ hours. So you could see that without the payload, the system is a bit lighter. We don't have so much components drawing a lot of power. So we can extend the flight time. Likewise, extend the communication range to 120 kilometers. Before that, let me just chip in this. The internal radio is giving us 30 kilometers. The booster itself is giving us plus 50 kilometers. So total, we are looking at 80 kilometers. That is systems configuration. But this 80 kilometers is terrain dependent. You can find yourself in certain environments and you may not get this because you may have certain man-made activities or non-man-made activities that will be attenuating your signal. So let's have this in mind. Okay. Ideally, we will focus 15%, factoring all terrain issues. So when you are deploying your system, even though when you add the internal and the external, we're getting 80%, we need to add our environmental issues of 15%. Or, sorry, deduct 15% of this. So that will bring us to what? 65 kilometers. So have this in mind. Okay? Fifteen percent of 80 kilometers. Okay. The flight characteristics is what?
That would be 12.5.
No, 15% of 80 kilometers is
That
what?
would be like 12.5 kilometers.
No. So you have 80 kilometers.
Not 15 kilometers out of 80, but 15%.
15% out of that.
Yes.
So you calculate it and then you subtract.
15% of 80,
And then you subtract it from 80. Yeah. Are we clear on that? So that will be what? 12.5. So now subtract the 12.5 from the 80.
It's 12.
Yeah, I think somebody gave me this. Somebody gave it to me and I wrote. It's what?
It's 12. It's 12, not 12. It's 12. So that's 80 minus 12. 68.
So 80 minus 12. So 68. Okay. So well, you gave it to me and I kind of put it there. Now, when we have the payload on board, which is about 400 grams, the maximum flight time with certain auxiliary battery support, we're looking at 2 hours 45 minutes. So auxiliary batteries are basically, you can have extra batteries on the aircraft, depending on how your order was with the system in terms of the configuration. And then you were looking at the 150 kilometer range. In terms of power, the system is using a LiPo battery, that is lithium polymer, a 4S lithium polymer with 23,000 milliampere or 23 ampere per hour in terms of its capacity. Let's look at the tolerance. The tolerance is very, very important. One of my biggest concerns in terms of designing this program is the environmental conditions here. And in terms of the environmental conditions, wind, weather, rain, in terms of its depth, we had to factor all of these things into consideration. And as pilots, you need to know how much the aircraft can take. So these are the tolerance level in terms of how much the aircraft can take. So with maximum takeoff and landing, we are looking at, in a very windy environment, we are looking at 9 meters per second in terms of the wind speed. When we are also in the cruise, it's 14 meters per second, which is 50 kilometers per hour. With wind or with rains, it can contain a little bit of little rains. So let's be very clear, the system is not rainproof. So the moment you are airborne and there's a sudden rain, use the little space you have to try and bring the aircraft home. Operational temperature is -20 to +45 degrees Celsius. And the maximum ceiling height is 4,000 meters or 4 kilometers. Jed, please, have you set the system up for them? Does everybody has the system? Okay, so we're going to take a little breather and then we're going to set up the systems. So we're going to, whilst Jed is assisting in setting up the software, I will give a little session on why we need these three softwares. So the first software that we're going to use is the Q ground control. The Q ground control is the ground control station software that controls the drone. At the same time, it helps us with the pre-programming of the aircraft, controlling of the payload, and anything that has to do with being able to fly the aircraft. The second software is the DeltaQuad simulator. So the DeltaQuad simulator is a basic software in a loop file that will be set up on your laptop. So basically what that means is that without the drone, you can still learn, you can still fly the drone, plan your mission, and when you are comfortable about the terrain, you can now take the drone outside to go and fly. Now, there are certain pre-marks, pre-standards that we need to plan our mission to meet these standards. Until we've succeeded in passing these pre-marks, the aircraft should not be flown. Once those pre-marks have been met, we can export our mission into Google Earth Pro and actually visualize how the flight will be in terms of obstacles that will be in the flight path of the aircraft. Yesterday, when we came, one of the things I observed is the pylons. So as pilots, you ask yourself, what is the average or the minimum height of pylons? What is the minimum height of a fuel storage tank? These are the environmental assessment that you need to do so that you have an average mindset in terms of what is the minimum height I can be and what is the maximum height I can go to. So that when I'm flying, I will not have any issues. So we will take our 10 minutes break whilst we set up the simulator. Whilst we do that, any questions? Because it looks like I'm the only one talking. Nobody is stopping me. So we're looking at the second session of the DeltaQuad. In this session, we're going to look at the subsystem. The system is broken down into 4 components. That is the airframe and the structural support, the propulsion system, command and control system, and the payload system. So the system is made up of 4 components. We're going to take a dive into each component or into each subsystem and what is in that system, what is the function of that system, and what you as a pilot, what is your responsibilities. So with the airframe and structural support, it's made up of 5 components. So we have the carry case, the fuselage, the carbon spars, the wings, and then the VTOL nacelles or the VTOL modules. Let's look at them. So the carry case, as you can see there, houses all the components for protection and transportation. So in no case should you put the drone under your armpit and say you are transporting the drone. The case is meant to protect the drone when you are transporting it. When you are done with the mission, put the drone back into it. That is the sole purpose of the carry case. The fuselage and the spars. So the fuselage houses all the avionic components. The payload, the battery, everything is housed in there. The spars provides the necessary support and connection to the wings as well as the VTOL modules. And that is what carries the entire weight of the aircraft. So it's very important. We have 2 types of spars. So we have the short one and then the long one. The short one is 850 mm. The long one is 150 mm. The short one goes in front. The long one goes at the back. Please do not interchange it. When you interchange it, you may force and punch the wings. When you look at the fuselage, it's divided into 3 sections. We have the battery bay, the payload bay, and then the avionic bay. The battery bay houses the battery component, the LTE modem, and then the front FPV camera. The payload component houses the surveillance camera and the gimbal system. The avionic bay houses the flight controller, the GPS, the compass system, the radio telemetry component, and all the electronic speed controllers that is controlling the propulsion system. The VTOL nacelle. So the VTOL nacelle, we have two types on it, or we have two different types. So we have the left side and the right side, which provides a vertical takeoff and landing support. So we have 4 motor. It's a typical X multi-copter configuration. So you know we have X configuration, and we have what again? In terms of multi-copters. Hey, just you've after your advance or you've forgotten everything. We have H configuration, we have X plus. So we have the X configuration, which is like this. We have the X plus, and we have the H configuration. Okay. So this is an X configuration. You can have a VTOL where you have a plus configuration or an H configuration. So let's have it at the back of our mind. So the motors are numbered in. So we have our clockwise direction and what? Counterclockwise direction. The basic principle is that whatever weight that we have to lift, which is the 6.2 kg, the resultant force, which is a combination of F1, F2, F3, F4, should be greater enough to lift the entire weight of the aircraft. And this is what? 6.2. Okay. If there is an imbalance in the force of one motor, where you have that imbalance, you notice that the aircraft that side will be trying to lift further and further than the others. And this is very basic from our mass is contributed by what? Payload, battery, fuselage, anything that is adding weight onto the system. If we don't fulfill this rule, there's no way we're going to get our vertical takeoff. If F and N is less than WG, we will just be on the ground and you hear the motors will just be spinning, trying to lift. In some cases, we will just lift up and all of a sudden, it will just come back to halt. So we don't want this. We also don't want F and N to be equal to WG. We always want to make sure that the resultant force is far greater than the maximum takeoff weight. So the manufacturer has done all these calculations. That's why we cannot alter these parameters by ourselves. The VTOL nacelle attachment provides these capabilities. So we need to be very careful when we are assembling it. Now, once we have taken off and we are transitioning to fixed wing, or we are flying with fixed wing, we are flying with what? The wings. And the wings is what provides us the ability to do the horizontal flight. So the vertical flight is achieved with the VTOL component, and then the horizontal flight is achieved with what? The wings. There are certain preconditioned takeoff parameters that is preset by the manufacturer. And when we change these preconditions, it affects performance. One of them is the manufacturer has recommended a certain takeoff height. And he has given the recommended height and a recommended height range. So let's say we have a 60-meter takeoff height. And then we have a recommended takeoff height, which we can go a little above the 60 to, let's say, 100. Right? If we decide to go above that 100, what then happens is that our pre-calculated flight time, which was pre-based on what the manufacturer has tested and said, listen, always take off at 60 meters. And this is the endurance that you can get. If we take off to maybe 200 meters before transitioning, we are wasting more of the battery, or we have already reduced our flight time by a certain percentage. So here the manufacturer is saying that if we go far above the recommended takeoff, we end up reducing our performance. But somehow we can also compensate for it. That is the wing component. That's the wings now what provides a 12 times more flight efficiency. So in basic principle, try as much as possible to keep your verticals at the recommended stage, and then you can increase your height with the fixed wing, because the fixed wing gives you more performance capabilities, because we are flying with a wing, we're not flying on power. The propulsion component is made up of 4 parts. So we have the battery component, we have the motors, the propellers, and then the smart charger. As I said earlier on, the battery is a 4S smart battery. It charges using the balance cable, not the XT connectors. So what you already know how we are charging the battery, this uses a different charging system. And we will understand the benefit of charging the batteries that way and why we need to do that. At 14.8 volts, the motor and propeller, so we have the lifting motors, and then we have the what? The pusher motor. The pusher motor is always is the one at the back. Okay? Yes, please.
I want to know if you can do away with the VTOL sometimes and just like the way we were using the one we built, just use the pusher. Is it possible that way?
It's not possible. So that is not how the manufacturer have designed the aircraft. But there are certain aircraft that the manufacturer gives you that freedom. But with this one, it is not possible. It has not been designed that way. So if you take out the VTOL module, then it becomes like an EB sense flight. So this is not, and secondly, when we start assembling the aircraft, you notice that that functionality has not been provisioned for. During the break, there was a question that was asked on the communication infrastructure. So I will take the liberty to go deeper into it so that we can all understand it, because it looks like I mentioned certain things and the understanding of where those things are is a bit different. So the DeltaQuad command and control system, as earlier indicated, is made up of the autopilot system. So let's all work together on this one. Made up of the autopilot system. The autopilot system has 2 parts. We have the hardware component, which is the board, right? The type of board that it's using is called CUAV NORA. So, as pilots, quickly put this one somewhere when you go home. Go and read about its capabilities. The software that runs on the board is the PIX4 VTOL firmware. We've already established that we have so many hardwares during our advanced training. And we also have so many autopilot software. Who can give me an example of one? Yes, autopilot firmware software. What software was running the fixed wing you guys built? Yeah? Yes, AgriPilot. So AgriPilot was the firmware, and the board you guys used was the Matex. The board you guys used was the Matex. So that is the first part. The second part is the ground control station. The ground control station is also made up of two parts. So you have the physical radio. Manufacturers are not really inventing the wheel. You can buy these systems, set it up. Some people call it H16, some people call it M16. So the M16 radio controller, that is the hardware bit, and then the software is the Q ground control. So the Q ground control software is what Jed is setting up on your laptops. You can set it up on Android, Linux, Windows, Apple platforms. This software can run on any of these. It's a cross-platform, which is developed with Qt. That is what Jed works with. The third component is the GPS system and compass. So the CUAV navigation system comes pre-component, as in the compass is attached to the GPS. It's not like separate unit. So everything is fused together as one. You have the air control unit. The air control unit is what measures the air pressure for the aircraft. And then you have the electronics for the pusher motor. Now, regarding the communication or the external communication, we have the LTE modem with VPN connection. LTE modem with VPN connection. Why do we need VPN connection? When we set up the internet bit of our modem, we do not expect anybody within the public communication infrastructure to have access to whatever communication that is going on between our drone and our controller. We could be working on very sensitive areas, and we want to keep this information private. So we go through the VPN infrastructure. And then we have our radio link booster that we attach to the M16 or the H16 controller to boost our signal. Let's take a very deep into the communication infrastructure architecture. Sub Lieutenant Boatin asked a question, and that question gave me an impression that I have mentioned some components and we don't know where these components are. So first thing, let's divide the system into two architects. So we have the air component and we have the ground component. Now, the air components, we have certain communication infrastructure that is only on the drone, and certain communication infrastructure that is on the ground. Okay. The first thing we need to look at is that how do all these communication infrastructure work? The M16 or the H16 ground control station comes with directional antennas. Sorry, omnidirectional antennas. These omnidirectional antennas gives us 30 kilometers in terms of its operational radius. And this is bi-directional. So this is the typical M16 controller. This controller has the Q ground control running on it. these antennas communicate on the 2.4 gigahertz communication infrastructure. And that communication infrastructure here is a bidirectional communication. So we can transmit to the drone, and the drone can also transmit to us. So we communicate two ways. Okay. Now, the second component of our communication, we can detach these antennas. And have our amplifier added to our controller. And this is what gives us the extended range. So all of this is happening on the ground. It is not on the drone.
Now, the internal one is 30 kilometers. Now, when you and the booster is supposed to be 50, so that is 8.
Yeah.
Now, when you detach the antenna that is supposed to give the 30 kilometer range, how then does you still get an 18?
So internally, these antennas are omnidirectional. Omnidirectional meaning that the communication is in some kind of the communication is some kind of like an apple shape, right? Now, once we take out this and then we bring this one in, we direct the communication towards, that's what you see there, the directional communication. Okay. Now, the antenna here comes with an external power bank that we add to this in terms of amplifying the signal. Okay. So in communication, it's just like, I'm going to use our churches as an example. So a pastor will pick up a microphone to speak. The typical human voice is around 4 kilohertz, right? So that conversation goes through the mic, which is 4 kilohertz. It goes through the mic, the microphone. Let's assume it's a cordless mic. So you have some kind of a receiver that receives the signal. Okay. The audio from the pastor's mouth, right, which is sampled at 4 kilohertz. There is something inbuilt in the microphone called transducer. This transducer takes the analog signal and converts it into a digital signal, right? So if the analog signal was something like this, the transducer now makes the signal some kind of looking like this. Okay. But this signal has a low frequency component in it. Okay, even though the human voice has that 4 kilohertz, but when I shout hallelujah, it's only the front people who will hear me. The back people won't hear me. That's why we put the microphones there, the speakers there so that they can hear. So this low frequency component will be transmitted. So let's assume this is x of t to this receiver, which is by the equipment guys. Now, when the signal is going through this small free space, there are members. Everybody is having fun. Shoes are making noise. So many things are happening. So there is some kind of error in this channel that is affecting the signal. So sometimes when you are there in the church, you hear or the microphones are so sensitive that it's picking all kinds of very little interference, right? So now I have my x of t, which is my signal, plus my error signal, which is the room or whatever, coming to this antenna. Now this antenna here receives these two signals, and then it enters here. Okay. Now what this system does is called some kind of a signal amplification or signal magnification, but it is a high frequency component that will take these two signals and amplify it. So this is my G of t. So at the end of the day, I have my G of t amplifying these signals. So the results now becomes x of t dot g of t plus g of t dot e of t. So you realize that my signal gets amplified, my noise also gets amplified. Now, this is the pleasant component that is good to our ears. This is the non-pleasant component that is not good to our ears. So we kind of put in certain filters to help us get rid of this signal. So you see the audio guys moving some things, trying to balance what is good to the ears and what is not good to the ears by trying to erase the noise component. So at the end of the day, in the speaker, this is what we hear. Now let's bring that analogy here. Let's assume that this is our drone. The drone is airborne. The drone is sending a signal, x of t. This is the free space that the signal is coming through. There are other things within the free space that is affecting our signal. So our x of t plus our noise is still coming to our receiver. But what I'm doing now is that I'm changing this receiver component and saying that I'm putting a directional antenna. So I've taken the omnidirectional antenna, putting a directional antenna. Now, what this directional antenna does is that it has a higher G of t compared to the original G of t of the antenna that came with the system. In antenna, we call it a gain, or it has a higher amplifying factor. That amplifying factor is higher than the original antenna. So with that amplifying factor, the signal can go further. But the only limitation is that I need to direct the antenna to the drone. But with the original antenna, I can be anywhere. I don't necessarily need to be focused on the drone's direction. So in a more advanced system, some manufacturers have what we call autonomous antenna tracking capabilities. So instead of me, the pilot, trying to track the drone, the antenna itself tracks the drone on its own. Right? So this time around, I have a bigger G of t because of the external antenna that I have added with the extra power. And this is now going to amplify this signal more, and this will give me more range. The moment somebody goes like this and comes like this, then you know that you've caused confusion. Yes, please.
Does it mean then that anytime you switch to the booster, you must always move where your drone is and always follow it?
Yes. Because and you will see the good thing I notice about this system is that you can have the booster on and then switch to internal. And then the moment you switch to booster, then you have to be a bit specific with your direction.
So does it mean that when you switch on, that's where you're going to get the 80?
Yes. Yes. So the 30 plus the 80 goes through. It's not like because you've added on now it's only 50. No, it's the internal plus the external that is giving you that.
So before you switch on, you said you can switch between both.
Yes.
So before you switch back to the antenna, it means your antenna has to be.
It has to be fixed on. You turn it off. You set it up before you turn it on. Yeah.
So it means with the booster, you can't set up a fixed ground control station.
The ground control station is always fixed. It's just that you, the human being, may not be fixed. So it's like when I have like for example, when we go to very mountainous environments to do mapping, our challenge is that we may find ourselves in a fixed location, and the drone may not be in a fixed location. The drone's position keeps changing. So you'll be getting signal interference. So a few augmentations we've done is that sometimes we may be in a very low area. So we kind of find something to give the controller a height, right? So that may be that, okay, now we sometimes we even mount it on the car so that we have a very good interception with the drone, okay? But you realize that this is fixed. But the signal is not fixed. The signal is going this way, going that way. But when you attach this, the direction of the signal is one way. Okay.
With a booster, so I'm looking at a situation where you are in a zigzag mission.
Mm-hmm.
It's transitioning from one end to the other. Does the booster have a specific angle direction? I mean, you should have maybe 60 degrees. Then, but when I'm facing this way, I mean, I get to know that okay, my drone is in this general area. I can cover it.
So this is a typical sectorized antenna. A sectorized antenna 1.8. So when I'm saying you are moving, it's not like you are going to know. It's sectorized. You can also look at our cell sites, like the telecom cell site. They have this type of antennas on it. It's not necessary. You have a certain field of view. It's sectorized. It's not necessarily. It's not like maybe you have to. No, it's sectorized. So that's a good question.
The further the drone flies, the general area is more
Broadened.
So if you are going to fly and plan a mission of 88 or 50 kilometers, you know that the 50 kilometers will generally be in this direction. If you want it in that direction, you can see. Unless if you are flying short, then you don't need to use the
You don't need this one.
this direction. You can come on and then you can also be there.
Okay. Well, sir, your question.
Okay, not that.
Okay, okay. Now, the frequency or the high frequency component doesn't change. So it's still the same 2.4 gigahertz, but we have an amplifying factor, right? So if it was only the internal system, we have the antennas here, we have our G of T in here. But if we change this to our sector antenna, there is a new parameter which is going to amplify our G of T again. And that is going to increase our range. Okay. Now, on the ground, for us to avoid interference, once the 2.4 gigahertz is what we are using to communicate with the drone, we cannot use the same 2.4 gigahertz to provide internet to the drone. We need the internet to do a few things. One, to load the base map. Two, to update the system. The beauty about this controller is that you can connect an Ethernet to it. So this, it has an Ethernet capability, so you can connect the Ethernet to it. And you can also hotspot internet from your mobile phone to it. But when you are hotspotting, you need to change your frequency to 5.8 gigahertz in order for your SSID to be seen by this device. 5.8 gigahertz. So this is where we will see yes. Yes. This is where we will see the phones that when they get missing, you know we've lost a half plot or quarter plot or so when we are doing the assembly, we will look at all that. Now, there is a functionality to have what we call a second screen. It's a functionality to have a second screen. So the second screens are where the laptops come in. So because the pilot has to concentrate in terms of what he's doing, the second screen provides direction to the pilot. So maybe the payload operator will only focus on the information the camera is giving, while the pilot focus on the aircraft. And then the second screen, we can, the same network that is giving internet to this, we put the second screen on the same network, assign the IP to it, and then we have a feed from the control station coming onto the second screen. So that is the purpose of the second laptop. Yeah. When we go on board the aircraft, we have the flight controller, we have the receiver component of the amplifier being here. We have the GPS, and we have our LTE modem, which is attached to the aircraft. So within the LTE modem, you insert your data SIM. So you buy the MTN data SIM, you bundle your data, and then you have it in there. The manufacturer will provide an access to a VPN connection and a profile setup, where you can set up the VPN connection and that VPN connection to the controllers. The reason being that we don't want the communication to go public. It's very sensitive, so we don't want that. The traditional telemetry receiver is here, which is bi-directional. It sends and then it receives, and it's attached to the very bottom where the pusher motor is. So once we start the assembly, we will look at is the communication clear now? Mr. Okansi. Let's go.
Does it have a SD card slot as well?
Yes. Okay, good. So the drone has two SD cards on board. One SD card is for recording of the flight controller log, which you use for geotagging in the case of the mapping of the drone. And if there is any crash or any issue, you use the flight log to troubleshoot the aircraft. We've already established that every consumer or pro-consumer drone that is running on the open source architecture has two types of log files. So we have the bin file and then the T-log file. The bin file sits on the flight controller on the drone, which is it's a big file. It has more details. It contains all the real-time processing of the aircraft information. And then we have a copy of that, which is the T-log on the controller. We also use the T-log file to troubleshoot the aircraft. If the aircraft is missing, we can use that log playback to do our search and rescue in terms of identifying our search radius. And then the other SD card is on the surveillance camera. So it records the high definition video which is on board the drone onto the SD card. And then a processed version of a certain quality is pushed to the ground control station. Why do we need to do that? Communication channel and delay conditions. Because we may not have perfect environment and we cannot keep sending such heavy bytes of data to the ground station. So you have the ability to change the transmission rates in terms of what you want to transmit to the ground. But the very high definition is stored on the SD card, which is on board the autopilot. Are we good? Thank you. The drone has two cameras on board it. The Nighthawk is the primary camera, which is the surveillance camera. It's only it's used when the drone is in flight and it's mapping. You have the FPV nose camera, which is used for the vertical takeoff. So when the drone is taking off, that is what helps you to see what is ahead of you. And then once the drone reaches that safe altitude, there's a way to retract the surveillance camera and then now use the surveillance camera to do your work. And then there is the operator software, which is the CCA3 software, which is used to operate the surveillance camera. It doesn't operate the FPV camera, only the surveillance camera. The capabilities, it's thermal, both RGB and live video. So this is not like you have to fly, come back and check your video. No. While the drone is flying, you are seeing your video real time. It has the ability to pan and also tilt. So it could be looking forward, you can tilt it to look down. And it has a 40x zoom range. You can touch anywhere on the screen of the controller and it will auto track whether the object is a static object or a moving object. It has automatic object following, coordinate acquisition. So you can see something on the vessel, sorry, on the sea or something, you can click on it and the coordinate position of that thing, you can get it. Whether in UTM or in a military grade coordinates, you can extract it. And then you have the GPS controlled camera. So maybe you can be sent a GPS coordinate of I was doing some research for Ghana Maritime. You know, the Adan area, they were dumping ships and other things. So they will only send you the coordinates and then we fly to those coordinates. Because sometimes you get there, it's a vast area. You don't know where they've dumped the ship is. So you just input the coordinates and then the drone will just fly directly to that coordinate.
The zoom you are talking about, I don't know whether it's this digital zoom.
Yeah, it's a digital zoom.
Optical zoom of the camera.
Yes.
Optical zoom.
Optical HD zoom. It's not analog. So this is HD zoom. It's not analog. So you can like, it's on the controller, you can actually zoom 40x to the object, and I think that is around 2 kilometers. So you can zoom on an object at 2 kilometers in terms of the slant range. And the object profile could still be around 5 by 5 meters. And then you have the onboard recording. Any questions? Okay, good. So we will. Yes, please.
The onboard recording, does it have a SIM card or SD card inside?
It has an SD card inside the camera. I think the default that comes with it is a 16 gig. You can increase it, but you have to be mindful of the class of the SD card because of the speed rate. So a typical class 10 SD card is what is recommended. So they've placed in a 16 gig SD card class 10. So if you want to change it to maybe 64 or 120, you can, but you have to be mindful of the speed of the SD card. Because if you put in a very slow SD card, the write rate of your data may not be that fast, and it will affect the quality of your data.
I don't know whether I use the camera spec in terms of megapixels. How very efficient.
Yeah, so this is an EOR camera. When I say EOR, so basically it's electro-optical. It's not moved by megapixel in terms of the sampling rates. So if you take a typical Phantom 4, Phantom 4 is not an EOR camera. It doesn't have electro-optical capabilities. It's purely pixel-based with packing density. So when you when you take a picture, depending on the height, you have a certain pixel that can be packed per certain centimeter region. But this is not pixel based. This is a typical EOR camera. So there's a big difference between the two. Yes. But the mapping one that you guys are getting, that is a pixel base. I think it's a Sony AR Mark 4, which is a 42 megapixel with a 35 millimeter, which is very wide. So with such a platform in the flight time, you can map not less at maybe a height of 150 meters. You can map not less than 500 acres. Okay, so we will start our third session rather, the assembling of the drone. So we're going to have 2 teams. It's quite wide. I think we've seen the dimensions. So let's split ourselves into 2 teams and then let's start the assembly. So we are going to cover everything to charging the battery. Okay, and we're going to go over and over and over. One thing that comes up in one of my engineering group is that when you've been flying Phantom and you're transitioning to these systems, because Phantom is that free and flexible, there are so many things we ignore as pilots. But these commercial systems requires a lot of attention. And before the class started, I was having a discussion with Mr. Herbert. He had also experienced it where one of his powerful platforms crashed. We've also experienced it before. And it is all about due diligence. You don't need to be afraid of the system. You have to make sure proper pre-flight checks are done before the system gets on board. It's just like like you are flying, you are picking an aircraft to somewhere. And imagine the airline company does not put in the right checks and maintenance. I mean, you will see the number of plane crashes that we will have in this country. It's all because of the safety standards, the checks that are being done and done properly. That's why these aircraft keeps going and coming and things keep happening. So we need to treat this aircraft as a manned aircraft. We don't have that luxury of the Phantom culture where battery, pakra, pipre, koko, two. We don't have that luxury. I mean, that's how the sound is. You hear the battery, pakra, then two, you are gone. We don't have that luxury with this system. And as I said, you are the pioneers. The standards you set today will determine the standards that will be used tomorrow. So we will not relax on it. Now, we're going to 2 teams. Within the 2 teams, we're going to have different structures in there. So we're going to have pilots, we're going to have our technical team, and then we're going to have our mission commanders. These positions will be rotated so that everybody can enjoy that role and enjoy that responsibility that comes with it. I think for the benefit of the Boundary Commission team, I will go over it and then we will look at that structure. We're just going to build 3 teams. So we have the mission commander, we have our pilot, and then our technical team. So the basic scenario here is that the mission commander is more or less the senior person who has a very broad understanding of the system and has received some kind of instructions to conduct whatever exercises. He's supposed to break down these instructions to these 2 people for them to be able to understand the mission objective. The pilot with the mission, with the technical team, is supposed to prepare the aircraft, do assessment of the mission instructions, pre-plan the mission, and make sure that the mission meets the objective of the aircraft. When the mission is completed and it comes back, the pilot and the technical team disassembles the aircraft, do the post-flight analysis of the aircraft, pack the aircraft, go through the log file, and then logs the aircraft and make sure that everything is fine and safe. Some of you may be here as students but may not be on the field. It's very clear. So when they are sending instructions, it has to be understood. Okay, so let's set the ball rolling. I will do the first demo, and then once I'm done with the demo, we will go through. I may need to borrow this table. Yes. So, yes. So we start with one system, but afterwards we will open the other system. One of the most important things when it comes to drone assembly is to pay attention to how the manufacturer delivers the drone and how certain structures or whatever have been put there. Mostly you take a picture so that when you're putting them back, you don't miss them or something like that. So the first thing we will bring out is our fuselage. So this is our fuselage. The fuselage has the airfoil rib connections here. So these connections is where all the power signal comes through to connect the subsequent unit. We have the hatch which protects all the components here. One of the things that this does is that it provides support to make sure that water doesn't seep in. And when you are preparing the drone, you don't need to close it because of heat. So when you are done preparing the drone before, you close it. So all what I have said, you can see them here. So here you have the autopilot, the GPS component, the air unit, everything situated in here. This is the receiver component of the radio, that's the telemetry unit. You have the payload here. You have the onboard processing unit with the SD card component attached to the camera. You also have the retractable system. So you see that when the drone is airborne, it retracts in terms of its operation. And then you have the battery bay, which sits on the Velcro. When you look here, we have the forward camera. Then we have our air unit where the air comes through the aircraft. So there's no way you should block these components. You have to give it as it is. Inside here, so I'm just doing it once, and then you will come and you will do it yourself. You have the LTE modem. So there's a Velcro that holds it together there. So you have to just remove that Velcro component slightly. Comes with a dual band antenna.
Cable is short.
There is a strap. So this is the model. So you can come and see it has the same slot. So you put the LTE in there. So when we are setting it up, we will take it out like this, connect it to our laptop, test connectivity. Is it? No, they are inside. These are omnidirectional.
So this is a normal model.
Yeah.
With an antenna on it.
Yeah, to increase the range. So just like your mobile phone. You see that you have what we call a patch antenna. The antenna doesn't necessarily need to be out.
So, but with our terrain, which is on the sea.
You don't need the 4G. That's why I gave the scenario use case. In urbanized environments where you have radio challenges, you may have a lot of 4G concentration. You can switch to this. So the Velcro, and then you just patch it back to see? What is your thing? So the SD card, we have one here. So this is where the logs goes to. So mostly you don't need to take you can take the SD card, put it in the adapter, and then copy it. And this is the type C where you can connect this to the flight controller to the laptop. And then there is the other SD card which is on the flight control, on the camera. So you see, this is an HDMI. So you can actually connect to a monitor on the ground to see the feedback. And then you have the signal cables coming in here. And then you have this here. So it's supposed to be here. The card is supposed to be cut inside. So this is the video processing storage where you have the SD card in there. The battery, this is the battery component, and then you have the battery stopper with the Velcro on it. As I said, this is a flying wing. The biggest problem with flying wing is that there is a CG, center of gravity, that has to be set here. If you don't put the battery to hit this corner and then you put the battery here, it affects the and two things will happen. Either you're going to have a tail heavy aircraft, so a tail heavy aircraft will be like this, or a head heavy aircraft. At the end of the day, when we put our middle finger somewhere here, we expect that the aircraft should be balanced. We don't want the aircraft to be like this or to be like that. So you always assemble the battery, put the battery in to hit the battery stop. The next is our carbon spars. So we have the 850 millimeter and then 1,500 millimeter. So what do we do with this? So shortest in front, back in the swing. Has gone all the way. Has gone all the way to even come into technology. One of the things you have to do as pilots, so I'm going to talk to the technical team, have this oil, see the sewing machine, have that oil in your kit and get some kind of a silk-like cloth, and then every time just put a little in the cloth. Because if you don't do that, yes, the friction widens the gap a little, and then as time goes on, it becomes a bit huge. So the technical team will be taking notes of things you need in your toolbox. The next is for us to work with the VTOL module, or the VTOL NASA. So it looks like even one table is not enough. So we have the male adapter component coming here, and then we have the other side going to the wing. So when you look at it, you realize that this is what connects, okay? And then this is what will be connecting to the wing. So if you check, we create the other one also here. Now, you notice that we have something we call the airfoil horns. These are the locking horns. Just going to bring my phone. Just last week, I got an image from a company in Hungary. They sent me a picture of somebody crashing a VTOL, all because the person did not lock the horns well. Wow, that's standing up. And this drone was 87,000 euros. So now, if you've noticed, it's quite a light material. So in your handling, you have to be a bit careful. When you need support to hold on to and attach, always go for the hard parts where they place this metal, this support. So please hold this one. So some will come and hold it and lock it. It's not advisable. Rather hold this hard side and then let that feel, let you see, now once you are done, observe the filing. Observe the filing. Observe the filing. Make sure it's filed exactly on the other side. If it is filed well, locking it becomes easy. So you hold and then you push it in. If it is not filed well, you can push and push and push to no go. So before you realize, you may break it. So now, I'm going to also use this side as my support.
Get the crowd. Get the crowd.
So you notice it's filed well. for every system, expansions will happen. So after some time, you notice that these things will be open. Now, once you are done with this, the next is to bring your wings. So watch how they are assembled in. So when you are putting it in, you see, and then the wing, avoid holding this side. It's a soft part. So always put the stress on the hard side. And then push it. See, when you push it, it gets down. And finally, you check if everything has ended in it. And you do the same for this one. So you see, I didn't hear it. I see that. I didn't hear that. So, yeah, it's a big bed.
And I see a problem.
Where?
So when there's a gap in the carbon, when there's a gap, and this one versus the alignment, there are P's in there that must slot.
Yes.
It may end up breaking. Yeah.
So always, when you slot, there is a stopper. There's a stopper. So you should always push it to feel that you've hit the stopper. Because if you don't hit the stopper, you realize that this side may belong, and you'll be pushing this side, and still you're not reaching the lock edge. So this is pure carbon. So this is how the aircraft looks like. And then when you are done, you have your lock. We've not come to the power side. We're just looking at assembling and
The one with the
yeah, locks. It has to fire. It has to fire. Okay. Yeah, this one is fine.
So, for example, in this direction, so in case you go outside,
there's a light
yes,
so just central.
so you are in flight and then the weather started.
So that's why we are here to look at the safety. Manufacturers manufacture it. Think about it like you bought your own private car. There is Ghana Road. Passing that Ghana Road. Don't do that. So fly it as if it's our personal thing. And we will protect the system. We will protect the system. The day I buy my fence, there is no way I will stay where I'm staying.
Let's go now.
Like I will not stay at that place with that horrible road. So me too poor, because we have to protect the car. Okay, so disassembly. We do the reverse of what we did. So now we pull out our ribs and we go one after the other. What you were mentioning, like what you're talking about, in some cases, some will start removing the nacelles here. What you are doing is that you are causing imbalance to the system. So you remember you distributed the weight in a certain way. So you don't go and say, okay, now I'm going to remove from this side. So you go the same reverse order how you went. So this one brings in the power. That's the condenser.
So when you miss this one fast, you may end up breaking the piece.
Yes.
That's
You
what
don't
I
need,
was trying to do.
yeah, you don't need to miss. And then you approve this.
Yeah.
So now you put the hard place. Good.
The guide.
Yeah, that's what I'm saying. It's important to pass.
So what some people have done is that they have also done their rod marking. So you can put some marking, then you know that this is where you're supposed to stop. Because once it becomes a general purpose tool, your attention to details will not be the same as somebody. But you can set certain guides.
I realized that there are stops with the wings. They actually have stops, so if you push this, it will definitely stop. So
Yeah, but I've seen instances where people try to punch their own hole. Because they didn't know, because what was Chrysler one of the, yes, but one, there was still a lot here, and she was still forcing to, but she forgot she had to push this one in further to have all the other side. So she was doing that. So the next, the VTOL module. And separate it. Separate it. And then you come to the rod. So you see, the rods get. So that was what I was talking about. Oh, you go.
Why can't you do the shot out of the road?
He wants to vent his anger on short people. We will let it pass. We will let it pass. So please, let's set up the two teams, and then we are all working as a team. Everybody should try their hands on it. Yes. So we have time. Everybody should try their hands on it, so that.
I think the other team
There's one thing we have to do.
I think we will push it technical.
all right. Let's see.
Let's take it to the car. I'm talking about in houses. Hundreds of dollars.
Tens of the commissioner is buying tens of thousands. These are the commissioner is buying.
Mostly it's dependent on the
Yeah, the governor is but that's the more reason why I do like you can't do away now.
I will talk because of something. Because of some of the things
The
that
camera you need sensors and stuff.
why we are talking about
What you are doing is wrong. Yes, I have put everything.
It changes for, don't forget that
Changes
this
for
one,
the
visualize
somewhere is image
science 1.4,
So is it 1.4 up or now?
no up.
Or you will think? It's not me say it changes for the.
yeah, but then you teach like of course.
No, he hasn't. But he was checking for people.
That's what I want to know. Is it
No, you see, no, it's for the. He was taking wrong. Everything was fixed before.
That is why it's now.
But and then
come. It's true. I know we are different. You know we are different.